Good afternoon, everyone. Today I'll be talking a little bit about how we can use concepts from observational causal inference to improve and audit machine learning models for healthcare. Honestly, I don't think I'll be able to get to the part of improvement a lot, but if you want to talk to me, I can have discussions offline. But to set the stage, the motivation of my work comes from the idea of learning health systems. There is no machine learning involved here. It's just a system where you're collecting data from the healthcare system, such as a hospital, about how things are going, how patient care is going, how clinicians are doing, and then using all of that data to come up with evidence of what's working, what's not working. Obviously, machine learning can be an integral part to doing something like this. And then you're going to look at all of that evidence and then put into practice better healthcare practices, maybe do better machine learning for diagnosis and things like that. So as I said, machine learning is a huge part of doing all of these tasks well. You can think of it as better collection of data with adaptive sampling, active learning, finding patient subtypes that you're treating at your hospital or your healthcare institution, generating evidence in terms of patient risk of specific diseases, patient risk of outcomes, how effective are the treatments that are being given, and then making better recommendations. And then, of course, all of this will make its way into better clinical decision making and even automating some operational tasks that only indirectly impact patient care. Okay, which means that we need to have like holistic systems when machine learning models are incorporated into such systems. So a lot of my work deals with the aspects of like, okay, we've built a machine learning model that does some clinical prediction, now what type of challenges. And a lot of that involves how do we do better evaluation, how do we think about what might happen to these, how they might behave in different situations, and whether we have sufficient evidence to understand that they are behaving as expected. And then, of course, when it goes downstream into deployment, there's a lot of considerations around safety and ethics of using such models in patient care. And today's example is mostly going to be how do we understand the reliability and robustness of these models, given that we have built them, we like their performance, and so on and so forth. The tasks that I'm talking about are going to be applicable in many supervised learning settings. Of course, we are using machine learning to do prognosticating of patients, say predicting their outcomes, or doing diagnosis, and everything that I'm going to say will be relevant to these aspects. I'm not going to get into the treatment efficacy part today, but as I said, I'm happy to talk about that offline. So when you're looking at machine learning models, you have to start thinking of them as part of a big system. So in this particular example, you have a machine learning model that takes some subset of features, let's say ECG data or echocardiogram data, which I'm going to denote by XM. Can everyone see my, yeah, okay. And then you're going to train a model to predict, say, heart disease risk of a patient. Your system of variables, when you deploy this model, it's going to interact with everything else in the system, such as when the model is retrained, or like even patient features like age, demographic, the manufacturing device that was used to collect collect your echoes or X-rays, so your sensing mechanism. Everything is part of that system, but you're looking at like a snapshot of that through the model. Okay? And so you trained your model, you're very happy with it, you decided this model is good and I'm going to go talk to another hospital and deploy it over there. And then you saw that the model actually is not performing as well as it did before. Okay, so now you want to really understand why this might be happening, and this is the kind of problem that I worry about a lot. So in this particular case, we talk a lot about explanations and interpretability, but here we are looking at it from a holistic system, and then what kind of diagnostic tools and explanations you might require are very different when you're trying to understand such a system. So here you saw that the loss of the model, initially script L, now is L plus delta, some non-trivial change, has happened, and I'm going to figure out exactly what is different between the source hospital and the target hospital that caused this change in my model performance. Okay, so that's the task we're going to look at. Canonically, if I just told you, okay, if I could find out and tell you there was a covariate shift, so all your features, somehow the distribution of those features is different from the source hospital and the target hospital, maybe you can do something like data augmentation to improve model performance. Some other issue might happen, such as there's a concept shift. That is actually telling you something different about what's happening. That's telling you that the way there's like a huge difference in how maybe the label is generated, or there's a concept shift in terms of what is even the concept label that you're actually looking at. Maybe you're diagnosing at different rates. Maybe you're there's a different clinical protocol that's being used for diagnosis or even prediction and so on and so forth. But then changing that operationally is a little bit of a harder task. But giving you that information will actually tell you what might need to change in the system. Maybe there are easier fixes like just pooling the data and training the model again. But you first need to find out what the problem is in the first place. Okay, so this is the kind of task that we care about. We're going to look at mechanistic explanations of model behaviors once you're happy with the model performance in maybe one domain. So now I'm going to narrow down and look at a toy concept model to give you some sense of how we actually go about doing this. So think of a system where you're only collecting 3 variables. My world is very simple. I measure the patient's age, I look at their echocardiogram, and I figure out whether they have structural heart disease. Okay? And so there are 3 variables, x1, x2, and y. That is the only thing I'm measuring. And I'm training a model that uses echocardiograms and age to predict heart disease. And the relationships between these variables is encoded in the form of this graph. Okay? So there's some randomness in the kinds of patients I'm seeing. So there's a random distribution of age. But of course, my echo is going to be influenced by how old I am. And of course, prevalence of heart disease is influenced by both of these features. Okay? The thing that this structure is giving me is knowledge of the joint distribution over all of these features, which is factorized into 3 mechanisms. These 3 mechanisms are the marginal distribution of age, the distribution of echocardiograms given age, and the distribution of having heart disease given all of this information. Okay? So I'm going to take now a machine learning model and then train it to predict heart disease from these features. Okay? I'm done with that. This is my joint distribution. I'm going to look at what happens when I put the model in the target domain. I saw this performance change. Now, the thing to remember is what can I expect is happening in the target data? Okay? So we are going to treat distribution shifts that are occurring from going from source to target as interventions in this particular causal system. Okay? And why can these interventions happen? They can happen because of a lot of things. Just clinical practices being different, clinical protocols being different, or just populations being different, which is an external source of variability in the system. Okay? So all distribution shifts are essentially interventions in this causal system. And now they are causing this change delta. And I'm going to figure out exactly who to blame for this shift. Okay? So that's a problem. And I'm going to represent it as follows. So hypothetically, let's say only the age distribution changes, then I'm going to denote this with this particular graph where I'm coloring the node that I think changes. And now the joint distribution over the data is such that nothing else in the system looks different except for my age distribution. Why can I do that? This is like a side effect of assuming this causal system. Each of the mechanisms can actually change independently without influencing any other mechanism. Okay? It's not a given that this was going to happen. This is happening as an artifact of me assuming the causal system. Now, if I want to place blame, then I want a method that will tell me exactly that the age distribution is different, everything else is the same. So that's what I'm going to see if I can develop a method that does that. A more interesting case is when multiple things are changing. Okay? Now here, the population is different. Maybe let's say it's an older population or a younger population. And then the rate at which you're collecting echocardiograms is also different, given the age. If both of these things are changing, then I want the system to be able to tell me how much each of these different things is contributing to my total loss change. Okay? And I want them to be in the proportion to which they actually influence the loss change. Okay? And so that is what we are going to find out. And the way to do this is as follows. We are going to treat these mechanisms as players in a game. And the way this game works is that a particular, so now it's a little bit confusing because there are 3 edges. It's intuitive to think of each of the edges as the mechanisms, but here the factor, each of these factors is the mechanism. And so we are going to place blame on the marginal of age, or x1, the conditional of echo given age, or x2 given x1, and then your concept shift, which is y given x1, x2. Okay? Now, each of these mechanisms play the game. When a player is involved in the game, they change the distribution from the source to the target. Okay? So here is what will happen. Let me actually go through this. Okay? So if only my age distribution is changing, the loss that I will have to look at is a loss where all of my other distributions are the same except for my age distribution. Okay? Now, similarly, if multiple things are changing, these 2 mechanisms have shifted to correspond to my target distribution, and then my conditional, the concept shift essentially remains the same. Great. I am pretending that these mechanisms are playing a game and contributing to the loss change. And what I'm going to do is I'm going to go over all such, I'm going to go over all possible combinations of such potential players. So I'm going to look at all the power set, all possible subsets, and I'm going to then average out the contribution of adding any new mechanism to play the game. Okay, so for each of these mechanisms, I'm going to now add a candidate mechanism where I'm going to say hypothetically what would happen if none of the players are playing the game, but now I added the concept mechanism. The loss will of course be such that only the player that is now added will be different. Let's say in the initial game, your age distribution was also changing, and now I added concept shift. So of course the loss will look like only conditional of x2 given x1 is the same, everything else looks like the target distribution. And in the last case, when everything is changing, my loss essentially corresponds to what I see in the target. Okay? Once I get all of these combinatorial options, I'm going to aggregate all of this and then place blame on this one distribution of interest. And I'm going to repeat this process for all possible mechanisms that change, and then that will give me exactly the how much each of the distributions is contributing to the loss change. But now to do something like this, I need to be able to calculate this loss for arbitrary combinations of these distributions or mechanisms. I don't have the data to do that. I only have data from XY samples from the source distribution, and I have XY samples from the target distribution. I don't have samples from a distribution where half of the things look like they are from the target and half of the factors look like they're from the source. And then the easy way to do this is to do importance sampling. I'm going to look at appropriate factorizations that have changed. And now all I need to do is come up with a weighting mechanism to weight my samples from the source distribution so that I can actually re-estimate the losses. Now, how do I get that? Either you can make assumptions about the type of distribution and actually calculate the densities and do the reweighting, or you can be smarter about it. We can just train machine learning models that will tell us whether the samples are from the source domain or the target domain, and the probability estimates from those probabilistic classifiers will tell us the weighting factor automatically. And so we can just do that, and then we'll get exactly the kinds of arbitrary combination of losses that we want to estimate, and then we just play the Shapley game that I told you about, and then we can average out all of these values, and that will give me exactly the attribution for every single mechanism of interest. Okay, so the nice thing is, of course, all of the attributions for every given mechanism will add up to the total loss change that you will see. If a particular distribution does not change, of course, the value of that attribution, I will not place any blame on that player, so the attribution will be 0. If a particular loss, you see that after adding that player does not change the loss, the attribution should be 0. And then, of course, if I'm going from source to target, and my attribution is a value A, from going from target to source, I should see the value of minus A, because it's going to decrease performance. So we kind of actually get all of this nice things, so we can trust the method to do what it's supposed to do. The key here is that I'm assuming that I've measured these variables of interest, that I actually have access to the things that I care about, and sometimes that's an easy problem, most times it's a harder problem. So that's like the key here that we need to look at, because I'm assuming that I have knowledge of a causal graph. However, it's the advantage of that is that you can get these graphs with collaboration with experts, and the motivation for that is because the way these variables and these systems are generated, we have by implicitly assuming a causal graph, we kind of have a notion of what to act on when we understand certain things change, because it's very natural for us to generate these causal graphs based on how decision making has happened throughout the healthcare process. But I can be naive about it, and I can say, well, I can also place blame on all possible marginal distributions in the data, or like assume a fully connected graph, and I can assume blame. But that actually, you'll get some numbers, but that's actually not interpretable in terms of how you can act in the system. With all the marginals, if only the age distribution has changed, and you remind yourself of the graph that you saw, because age has changed, it's going to affect the marginal distribution of generating echoes. It's also going to affect the marginal distribution of heart disease. So you're going to place blame on every single variable in the system, and you're not going to know exactly why certain things are changing. So it's very important that you have a good sense of the data generating mechanism, or basically the whole system, to understand why things are different across. And this is a way to actually get to a point where you can statistically do this robustly. Okay? The other thing that it actually points out is, as I mentioned before, you're changing these mechanisms independently. And that's not like a trivial thing to assume. You can only do this because you're assuming like something is behaving like an actual causal system. Okay, so we did something like this. Does it bias something interesting? So we can look at some use cases where we thought it was, we got some cute results on what we can actually do with it. So let's say there's a machine learning model that takes patient vitals, demographic information, whether they referred themselves to an elective surgery, and then we are going to look at their mortality outcome 24 hours or 48 hours after their stay. And so we took the 4 largest hospitals from the Midwest, and then we looked at a model that actually oversampled younger people, and then we trained a model to predict their mortality. And now we are going to test this model in 4 largest hospitals in the southern region of the United States. Okay? And we are going to explain the mean squared error between the labels and the probabilities estimated, which is called the Breyer score. Now, as you can see, you went from a source to a target domain where the error actually increased. And now I'm going to look at exactly what are the things, the distributions that changed across these domains. And on the left here, you can see all of these top shifts are sort of conditional shifts occurring in the data. This essentially implies that the process differences across hospitals are quite significant, and they are affecting how the model might perform. The last one is something like age, which I think we can easily control by either oversampling or undersampling a particular population. And so if you do that, you can actually then take the data, rebuild a new model, and then you can actually see the performance differences go down. And then, of course, the blame that you had placed on age kind of goes down, and some other things try to now surface up, such as demographics, started becoming an important factor here. So you can repeat the process depending on what actions you can take in the system, and then you can improve. The only thing about that subsampling, did you have a question? No, we did not consider specific type, just whether or not they had surgery. So yeah, so now you could basically repeat this process. The only downside is that you saw the Breyer score change even in the source domain. So maybe there are better actions to take rather than just augmenting the data or subsampling the data in a particular way. You can use this to check whether your robustness models are behaving the way they are supposed to behave. So in this particular example, you want to audit a particular robustness method called group DRO. If you're familiar with it, if you're not familiar with it, colored MNIST, you've seen this example multiple times now, is a data set where you are testing for potential spurious correlations in your model, where the color is basically highly correlated with the digit label, and that causes the model to rely much more on color than it should. And lots of methods have been trained to actually prevent this from happening. Group DRO is one such method where it's essentially going to pretend like the data is coming from a mixture of M groups, each indexed by G, and it's going to basically try to optimize only the worst performing group, which is the group where the correlation does not essentially hold. And so it should technically remove this reliance on spurious correlation. So let's see if it does that. We take a model that does not do all of this group DRO business, just empirical risk minimization. You can see that as the association between the label and the color goes up, the performance is of course going to go down. But all of the blame from the method that we run is going to be placed on that conditional distribution of interest. Remember, there was no misspecification in the graph that can change the results. But then you decided to check what happens when you actually run a robust method. Now you can see that the performance difference going from the source domain to the target domain actually went down. So the model is working really well. In the target domain, there is no such spurious correlation. And the blame for the conditional also basically is almost negligible. It's essentially all noise. Okay, so these are the kinds of things you can do and the kinds of tools we even need to get a good understanding of whether these models are behaving the way we want them to behave. Okay, so I don't know how much time I have, so I'm going to basically end by saying we kind of need such sophisticated tools. We are now looking at how this might do if we don't measure all variables in the system, or we can use these for equity audits, and that's something we are working on now. For us, it's exciting that we're not making very strong assumptions, but one of the things that I think is that interesting for this audience is while the method we showed it in the context of a specific healthcare task, I think there's a lot of generality to how we can use this to understand differences in mechanisms across populations. You don't have to explicitly explain a model. You can actually use it to understand just data distribution shifts, even without a particular model. And that's, I think, the more interesting aspect of this, because you can use it for discovery type tasks. All right. With that, I'm going to end. Come talk to me about some of the other causal stuff that I'm doing. I'm happy to chat more, and I can take questions.